Drew, I'm wearing this hat for you. I told you I'd wear it today. Okay, what we're looking at here is mechanical advantage. And normally this is something that, we may hit on a year, we may not. But you might have actually talked about mechanical advantage back in your middle school years. In middle school, you talk about mechanical advantage on how simple machines, which we have the 6 simple machines here. We've got a lever, a pulley, a wheel and axle, a ramp, a wedge, and a screw. These simple machines allow us to exert some amount of force and to get a larger amount of force out of it. The trade-off is we have to use longer distances to do that. So these simple machines are very, very nice for us, but essentially it just changes the amount and the direction of work. And that mechanical advantage is what has allowed humans to do so much. There's no way that I myself could lift a steel I-beam, but if I get enough pulleys and a chain that's strong enough, of course I can. We built a bunch of machines in order to allow us to build the world. Or build the modern world that we see. So these simple machines are very, very useful. You use wedges whenever you're splitting wood. Archimedes screw is used to lift water. Ramps are just used to move objects. Like they're very, very useful. We see them all the time. Now, when we're thinking about simple machines, the 2 terms we really are thinking about are mechanical advantage and an ideal mechanical advantage. They're similar, but not exactly the same. Our mechanical advantage is looking at the ratio of resistance force to an effort force. And we think about this effort force is the force that is supplied to the machine, okay? So this is physically like what you're exerting on the machine, right? Maybe you're pushing down on a lever, okay? So out here, if you're pushing down here, this would be the effort force. On the other hand, it is a ratio of that resistance force to an effort force. So we are the effort force here. The resistance force is what the machine is actually doing. So if this lever here on this fulcrum, this pivot point, is lifting up, this is the resistance force, F sub R. And mechanical advantage, we just define as the ratio of that resistance force, that output, to the effort force, that input. So instead of writing FR, I'm going to call this force out. Like this is the output of the machine itself. And for FE, the effort force, what you're putting into the machine, I'm going to call this F in. And what we can quickly see there is that mechanical advantage then, which we'll just call MA, that's going to equal the force out over the force in. That's our mechanical advantage. And in using these simple machines, we can get a larger output force than an input force, which allows us to be able to lift these heavier and heavier objects, to move them more easily, to split woods. We essentially made ourselves stronger through the use of machines. Now, one of the issues in these simple machines, and like I said before, while we're getting more output force, we have longer distances that we have to travel through. So if you take a look at this, the lever here, this lifting is only lifting a small amount. If we imagine that this lever was sitting on the ground like this, it's only lifted up a small amount. But you have moved it down a much larger amount here. You've had to use your effort over a longer distance, but you're getting, as a result of that, a larger output force over a smaller distance. So even though we have less force we're putting in to get nice outputs, we have to use that force over a longer period of time. And one of the issues with this is these simple machines are not perfectly efficient. Some of our energy is going to be lost there. In an ideal machine, all of your input work is going to be transferred to output work. But that doesn't happen often. But in an ideal world, what we can actually think about is for an ideal mechanical advantage, what we would have is that the distance we put into the machine over the distance out of the machine, that is going to be our ideal setup there. So what we have now is a mechanical advantage of F out over F in, and an ideal mechanical advantage, the distance you're pushing into it versus the distance output there. And when we think about this distance into it, what we're thinking about here is this idea of like for the wedge, we might have to drive this wedge, some distance in, and as a result, we're going to get some distance out here. Okay, that's what we're thinking about for the distance in and distance out. Now, for our efficiency, we have already talked about that. This idea of simple machines, we're doing useful work, and because we're doing useful work, and we know work is a dot product, F dot delta x, the force dotted with the displacement, and if that cosine angle is 0 degrees, and this is just F times x, we are thinking about works here. And we do see that we have forces and distances. Those are the primary things we're thinking about when we're doing this useful work for mechanical advantage and ideal mechanical advantage. Our efficiency is going to be calculated, E, as the work that you get out of the machine over the work you put into the machine. And then if you want this in a percent, you would multiply it by 100, because that would then give you a percentage there. Okay, so this is an efficiency. It designates what is your output work over your input work. And if your output work is equal to your input work, then you are a perfectly 100% efficient machine, and we really don't have those. The only time I could say that this would be perfectly efficient is maybe if you were like lifting a box directly up, but even then, you're spending energy in terms of just fueling your body, so nothing's perfectly efficient. If you had a perfectly efficient machine, though, or if you just wanted to find the efficiency of a machine, something that had a mechanical advantage and an ideal mechanical advantage, then an efficiency of a machine can be quickly written as the mechanical advantage over the ideal mechanical advantage. Once again, times 100 to get yourself into a percent. And that makes sense there, because if you take a mechanical advantage divided by a ideal mechanical advantage, you have F out over F in over D in over D out, which means that whenever you move these equations around a little bit, what you're going to get is F out D out over F in D in, which is work. Okay. Instead of looking at delta x's here, we're just calling these d's displacements. It's a distance. It's whatever you like to think of it as. So same ideas here. We are just seeing work and work. That is for any machine. Okay. So this is the idea of just simple machines, how we can do useful work using objects such as levers, pulleys, wheel and axle, a ramp, a wedge, or a simple screw. We can take these simple machines and we can make them more complicated by combining them or linking them together, or having multi-pulley systems and all sorts of things like hydraulics. But in just general, these are the main concepts that we're using for that. In our next little video, we will see just how we can go ahead and put these equations into figuring out the mechanical advantage, the ideal mechanical advantage, and efficiencies of some simple systems. But until next time, we are finished here. Adios, and take it easy.